Okay, so for this problem, we're given a Python file which appears to generate a multi-prime RSA key that should be in some way inherently insecure. They gave us a couple extra methods, including one to compute the next prime, modular inverse, and extended Euclidean algorithm. And then they used the PyCrypto library as random. So we're led to believe that that's pretty secure, so we shouldn't be attacking the random. So taking a look at this real quick, looking at how the primes are generated, the first one is it's somewhere around 2 to the 251st, which is pretty large, and I pulled up Python and checked how large that was just to see if we could do any kind of brute force. It's, approximately 3.6 times 10 to the 74th, which is probably too big. So brute force in that way was out. But then if we take a look down here on how the rest of these primes are generated, we can see the first prime is that random one of the order somewhere around 10 to the 74th. And then the second one is just close to about 10 times that, and the next one 10 times the previous, and the next one 10 times the previous. So it gets you thinking if you can make an approximation about the original prime based on n with the knowledge of how the other primes are generated. So if we go over to Paint real quick and do some thinking about how this value n is actually comprised as the product of these, we can come up with this trivial approximation that n is approximately p multiplied by itself 4 times there. And then if we look at this, we can see this 10 gets compounded onto itself multiple times in a row, such that it's multiplied times 10, and then times 10 times 10, and times 10 times 10 times 10. So that's 1 plus 2 plus 3 is 6. So n is approximately p to the 4th times 10 to the 6th. From this, we're interested in getting one of the primes so that we can create the RSA key again. So we just need an approximation for p, so we just solve the equation. So p is approximately equal to the 4th root of n, and I'll use 2 division symbols for integer division over 10 to the 6th because we're interested in integers. So given this approximation here for p, we can write a script to assume this is close to where the prime is, find the prime, and then reconstruct the RSA key. So the first thing you might notice is we need an integer 4th root function. 2018 and being CTF, we don't have to cite sources, so let's just hop over on the internet and good old Stack Overflow post for integer root function. And this appears to use some kind of binary search, so it should be like logarithmic complexity and should run fast enough. So, copy paste, walk over to a new script, comment out the old code. So now we got that integer root function, and we'll make a guess for p, which is just using that function to compute the 4th root of n over 10 to the 6th. And then that is an overestimate actually, so we're going to go backwards. I wrote this other function last prime, which does the same thing as next prime, just goes backwards 1 instead of forwards 1, and find that prime p, the first prime where n mod p is 0, meaning that p divides n. Then compute the other primes using their next prime function as shown. And now we're just doing simple RSA. So we compute Euler's totient function, which is, for a bunch of prime numbers, is just going to be the product of 1 less than all those prime numbers. And we have a known public exponent, so we just compute the private exponent. I didn't check if their mod inverse handled the negative number case, so I just used the extended Euclidean algorithm, took the value out of the tuple, then corrected for it being less than 0. And now we have private exponent and modulus n, so we can go back from the ciphertext to the message. So m is the message is the ciphertext to the power private exponent d modulo n, and boom, we have that as a number, but we needed this ASCII text. There's probably a library call for this, some fancy Python one-liner that requires looking up a bunch of stuff, but I decided on 20 seconds of thought, so make a string. We're going to be appending this value to the beginning of my string each time, and just taking the string mod 256 to get the least significant, and then dividing it by 256 to move that over. Could have done this with bit shifts, did it with division, print the flag, and we're done. So we walk over to Python here and just go ahead and run the script, and there's the flag.